Hello guys, so I'm preparing this lecture again as part of giving you a bonus further exercise on TensorFlow and understanding what happens under the bonnet in TensorFlow. So what we're going to be comparing is we're going to be using, the usual, we're going to first use class-based, TensorFlow linear regression model. And then we're going to be comparing using gradient tape and the conventional model.compile, basically, just so that you have a better feel of what's happening on there. So I'm going to call this regression model with gtape and compile. Okay, so shall we call it that? All right. So I'm going to, in the first instance, import TensorFlow as TF, okay? And maybe I should basically make this a bit larger, huh? What the hell? Yep, okay. So I'm going to do import TensorFlow as TF, and I'm going to need NumPy. Import NumPy as NP. Okay, so we got our libraries imported. Now, what I'm going to do is to create a linear regression model. Yeah, so making uh, making a simple linear regression model with um, class oriented with CLM. So class. Okay, so I'm going to say class. Okay, class linear regression, and I'm going to inherit to this from TensorFlow.keras.model. Okay, and then define init, define init self. Okay, and what do we need to do? Super, so that we get everything relevant inherited, basically all the attributes and everything to the inheritor. Super init. Okay, so that takes care of this. All right, now linear regression. What do we deal with a linear regression? We're going to be having some weights and some biases. Yeah, so I'm going to say self. Well, simple linear regression is there is a weight and there is a bias, of course. So self dot weight equals TensorFlow dot variable y variable, or because it's going to be getting updated or changed. Self dot what do you call it? B bias equals TensorFlow dot variable, and just initialize it like that. Okay. Now we're going to be using the def call, to allow forward propagation and like sort of flow of the data. So different call. It's going to be self x. All right. What are we going to do? So these are the weight is set as 0.1. B is 0.1 as well. So define call x. What is x? X is what we are going to be feeding into this model, isn't it? So if you have an x, think of what is a linear regression model. Okay, so return, of course, you're always used to ax plus c. Okay, in other words, it's weight times x plus the bias. Yeah, so the usual math you have learned is ax plus c. I'm just going to call it wx plus b. So self dot w multiplied by x plus self dot b. Okay, so that's the linear model. Okay, a very basic one. I hope, yeah, I think everything's right. Okay, now we're going to, so this is our model. We're going to now make two instances of it. Okay, let's just run it like this. Okay, so I've made my model and I'm now going to make two instances of it. So I'm going to call model with gradient tape equals linear, come on, linear regression. Okay, and model, another instance of it, model compile. Yeah, I'm just naming these. I think model compile is again the same instance of linear regression. Okay, there we go. So we made the instances. Oh, what did I make wrong? Model tape super init. What did I do wrong here? Super. Ah, is it there? Oh, int. Sorry, my bad. Okay, always check your spellings. Okay, so yeah, I'll just make an instance, two instances of this model, the very basic model that we created. Okay, so let's create some variables that we're going to be playing above it. So let's say xtrain is going to be np.array, and shall we say 1, 2, 3, 4, 5, and 6. Yeah, and dtype is going to be dtype equals np.float32. Oh, float32, and on ytrain is going to be np.array, and shall we just say double it, guys, then triple it, yeah, 3, 6, 15, 12, no, sorry, 9, 12, 15, and 18. Okay, so just to make it really simple for us to understand, dtype equals np.float32. Okay, so that's our x and y values. Okay, so the usual using the compile model, let's go and use the compile model first. Yeah, so we're going to say model compile. Okay, dot compile, of course. So remember, this compile, I could have named it Mickey Mouse, yeah, but I just used underline compile, to be relevant. But this is the actual method I'm calling. So dot compile, let's say optimizer. Optimizer is SGD, stochastic gradient descent, and loss. What loss do we use, guys? MSE, mean squared error, and metrics equals mean absolute error. Oh, come on. Mean absolute error. I've done something wrong. Why is that in red? What did I do wrong? Oh yes, that's fine. Now, okay, so compile the model is compiled. What do we need to do is just fit model dot fit and we're gonna say x train y train epochs equals 100. Yeah, and shall I say variables equals 0. Variables equals 0, so I don't see, loads of report basically coming out. So model compile dot fit. Yeah. Okay, and I get an error because I have a capital X here. Variables. Oh, well, there goes my spelling. Okay, so that's that basically. All right. Let's see, after running this, if you recall, I preset the weights. Yeah, I did preset the weights. So presetting the weight and presetting the bias. Okay, so you remember we had preset them to be 0.1. Yeah, so what do you think are these values now? So if I say model compile dot w, that gives me the weight. Yeah, but remember it gives it in form of a tensor. All right. It's a TensorFlow variable. So if I say dot numpy, I should get the value. And why don't I make it even more nicer and say print this? Right? And I can also say print model compile dot e dot numpy. Okay. As a matter of fact, let's just be more professional. Yeah. The updated weight. Okay. This is better. And f string the updated bias. Okay. So if you recall, we started with 0.1, okay, and obviously this has gone through training for 100 epochs, and it has come up with these weights. So, but in reality, I mean, that should be as low as possible. We don't really have a bias here, yeah. And the relationship should be really 3, yeah, because on purpose, I tripled everything, yeah. So, what if I do 1000? Do you think it's going to make a difference? Of course it should, okay. So if I say print, as you can see, it's reduced. So further epochs we carry out, like our model is going to be trained on. Well, I'm sure you know all of this. We have covered this sort of stuff before. What I like you to learn is, one is this approach, using this class-based writing of functions, and the other is for what I'm about to open up next. Now, let's go with gradient tape, okay? So we're going to go with gradient tape now. Using gradient tape, all right, so we need to first define our optimizer, okay, an optimizer for gradient tape model. So we're gonna say optimizer tape, yeah, optimizer tape. Optimizer tape is TensorFlow dot keras dot optimizers dot sgd. and should we put the learning rate? Well, leave learning rate for the moment, okay? So I'll choose a optimizer to start with, okay? And then I'm going to create that loop to train my gradient tape. Okay, so I'm going to say for epoch in range 100, okay, for epoch in range 100, and then I'm going to say with TensorFlow dot gradient tape, where is it? With gradient tape oh, as tape, with gradient tape as tape, preds equals model. What model? Model tape, the instance that we made here. Model tape. Yeah. Model tape. The model tape. Model tape work on X train. Okay. So the model gets these X data. Okay. I mean, we need to do this manually, obviously, yeah? So we are not having the luxury of model.compile. We want to do this manually. Okay, so preds are that. This is on the first epoch. How do we compare this? Well, we need a loss function, yeah? So remember, we make predictions. Now we need to calculate a loss, okay? So we calculate a loss, okay? Loss equals TensorFlow dot what is mean? A reduce mean, isn't it, in TensorFlow? What's this thing with TensorFlow? You know, reduce this, reduce that. Oh, anyway, reduce mean. TensorFlow dot not reduce a square. TensorFlow dot square of what, guys? Preds minus what? Y train. What is this, guys, really? It's manual mean squared error MSE. Okay, mean squared error. So we make a prediction on each epoch and we compare the error between the Y train, which is the real basically values, and these are predictions, and we are generating a loss. We are basically generating MSE on every epoch. Okay, so that's all it is so far, nothing complicated. But this is where we're going to, sort of training our model and everything. So what are we going to have? We need to have gradients, isn't it? So gradients, yeah, equals gradients equals tape, yeah, with tape dot gradient, yeah, and gradient of what? So we have a loss value, okay, and then model tape dot trainable variables. You might be like, Ali, what is this model trainable variables? Let's just look at it separately. Model tape dot trainable variables. Okay, remember we have already set these trainable variables. Where did we set these variables? Yeah, there we go. This is our model's variables. Okay, all right, so gradients, we're using the tape.gradient, okay, to calculate the gradients of or loss in association with our variable. So we get a set of gradients. Now we need to optimize, right? So optimizer, tape. We're gonna now use this, yeah? So here we calculate gradient per yeah, epoch. And then what? What do we do here? We're going to now optimize, yeah? So we're gonna say optimizer tape dot apply the gradients. Apply tape dot apply gradients. The reason it's not coming is because I still haven't run this. I should really have run this in a separate gradient dot apply gradients and gradients what? So we need to zip or gradients with our trainable variables, yeah? So zip gradients and or models trainable variables, okay. Yeah, that's about it. So let's just and here we are applying the optimizer, right? So hopefully everything should go fine. So technically this is like 100 epochs. I'm just going similar to the other model. So let's just run it. Oh, and I got an error. Zinp. Oh, sorry. But you're used to me making all these mistakes with typing. Okay, that's fine. So it's done. Let me get rid of this. So now this model is trained as well. Yeah. Shall we do the same thing? So model tape dot trainable variables, yeah, 2.88 dot numpy, sorry, numpy. Oh, come on. List object has model dot trainable. What did I do wrong? Oh, sorry. Wait. List object and model dot model dot w. Sorry. So that's the way, and then model tape dot b was it? Yeah, numpy. Okay, so and that's the way. Let's just print it as before. Okay. Oh. Print a string here updated wait for tape model. Okay. Let's just do that. And I really think and print f string print f string. Have I got that right? There is no. And now print f model, and we're gonna say the updated wait, the updated bias for model tape. I'm going to do that. Okay. Now obviously This is with 100 epochs. What if I go with more epochs, guys? I should be able to match that. Okay. Is it the same? It should be almost the same. Yeah, roughly quite similar. Yeah. What if I was to go with 2000? Can we make better improvement? So this is going to take a bit longer, but I'm hoping that we can improve on these weights. Yeah. So this is going like really, really, really small. Yeah. So remember, this is times 10 to the power minus 5. Okay. And obviously, you know how we can make a prediction, right? Yeah. So shall we say, what was it? Tape, model tape, dot predict, and what are we going to feed into it? Shall we just, let's just feed the same thing, you know, because, yeah, I'm going to feed that to it. That'll be cool. See what does it give us. Oh, all right, so model tape dot predict, okay, well, there we go. And model compile, was it? Yeah, let's call it model compile dot predict, and just the same thing. Okay, obviously this is a more accurate model, you know, because we trained 2000 epochs, but more or less, you know, we are almost getting the same thing, isn't it? Yeah. So guys, the only reason that I did this video was again to get you guys more comfortable. As I said, I don't know if you even need to learn these at this stage, but I thought it would be good for you to learn what's happening under the bonnet, you know, when we have more other classes and, you know, you are sort of making instances of classes. So just a recap, we made a linear regression model, and for this, we inherited from TensorFlow.keras.model, okay? So when we inherited from there, okay, we defined a weight and a bias, okay? Then we went and defined the call method associated with TensorFlow for the flow of the data, basically, where we gave a return. You know, this function calculates something, weight times the input plus a bias. Yeah, it would just return that. So when we make an instance of our model, we are making an instance of this. Okay, we are just making an instance of this. Remember, before we would be importing a model, basically, maybe from, I don't know, scikit-learn or whoever, or TensorFlow. Here we just sort of made it, but we made it by also inheriting from keras.model. Now we make two instances of it. One instance, we want to use the straightforward .compile and .fit method, which I'm sure you're all very familiar with. Okay. So model.compile optimizer, we define a loss. All of this is done under the bonnet automatically for us. And then we do a fit with our X train, Y train, number of epochs, and these verbos, again, just in case some of you have forgotten, if I oh, if I don't put verbos, you see I was just trying to avoid all this, yeah? So that's why I put verbos equals 0. Verbos equals 0. Okay. Oh no, I sort of regret doing it. No, anyway, I'm glad at least you see what's happening. So clear output, yeah. And then I basically printed the weights. Do you remember? I mean, if I was to do just 10, okay, right. Where did I get that? Oh, it's because it's already trained. Yeah. So that was a very straightforward, dot compile and dot fit. What I really want you to sort of again appreciate and understand is when we use the gradient tape method. So here it's far more, your hands are getting really dirty. So you define your optimizer, then you define all your epoch, okay? So yeah, basically that's how it works. So TensorFlow, Pred's model tape, X-train, yeah. So we are defining certain number of epochs, okay? So we are creating a for loop basically. And with gradient tape as tape, Preds equals model tape. So in the first instance, this model is not trained or anything, yeah. It will go and calculate spreads by using the initialized 0.1 and zero point 0.1 weight and bias. It will first do that. And obviously, it's going to create some form of junk. Then we need to calculate the loss. So we calculate the loss by saying TensorFlow that reduce mean. Yeah, we calculate the loss, which is mean squared error. We use the reduced mean, which is mean of a squared of the errors. Okay, so we have a loss value per epoch, per epoch. Once we got this loss value, okay, once we got this loss value, then we have to calculate the gradients. So how do we calculate the gradient? Well, now we have the tape doing it for us. Tape.gradient and loss model tape dot trainable variables. Okay. The trainable variables are the W and B, okay? And the loss is this. So it's calculating the gradients. And now we are going to adjust those, yeah, by, the method of backpropagation and all that. So optimize that tape, which we already defined. We're going to use the optimizer to then apply these gradients and adjust the weights basically. So zip gradients and model.trainable variables. So we are training, but this is basically optimizer to train the weight and bias value, or train them, update them, whatever you call it. Okay. And once that's done, so everything is done manually here. Well, partly manually, of course, we are still using the gradient tape, and our model is doing that. So, of course, this gives you a more versatile way of designing models. This is really basic, but I thought like it was a good sort of presentation of so that you know what's happening under the bonnet, when you're writing these models and all that. Hope you enjoyed it, and all the best.